This is a revision video for AQA GCSE Chemistry or Combined Science Unit 8, Chemical Analysis, which is all about how we can use chemistry to figure out what a substance is. Remember, 40% of the marks in your GCSE Science are for being able to recall the facts from the specification. So this is a summary video to make sure that you do know all those facts, and then you can go on and use exam questions to help you practice applying that knowledge and using it to analyse data. In chemistry, a pure substance is a single element or compound that doesn't have anything else mixed in with it. You can identify a pure substance using its melting or boiling point. So for instance, we know that pure water should melt at exactly 0 degrees and boil at exactly 100 degrees. If you have a sample of water and it actually boils at 102 degrees, that tells you that it's got something else mixed in with it. A formulation is a special kind of mixture where it's been designed as a useful product. So if we take an example of this, if you have, say, some Calpol, it's got a particular amount of the medicine in it, it's got a particular amount of sugar in it to make it taste better, and it's also got a particular amount of the different materials that sort of hold the whole medicine together. 7 examples of formulations are fuels, cleaning agents, paints, medicines, alloys, fertilisers and foods. Those are all listed in your specification, so they could come up as like a little multiple choice one near the beginning where they ask you which one of these might be a formulation. Chromatography is a physical separation technique used to split apart mixtures of liquids or gases and analyse them. When you do chromatography, you're always going to have a stationary phase and a mobile phase. So the stationary phase is the one that doesn't move. In the paper chromatography that you did for the required practical, this is the piece of paper. The mobile phase is then whatever does move. So in the required practical, it's the solvent that you put that paper in, probably water. Substances are separated in chromatography according to how well they are retained by the stationary phase. So for paper chromatography, this is all about solubility. The more soluble an ink is, the further it will travel up the piece of paper. An RF value is a way of putting a number on how well something is retained. The RF actually stands for retention factor. An RF value is calculated by using the distance moved by the substance and dividing it by the distance moved by the solvent. This means that it's always going to be a value between 0 and 1, because there's no way that the substance can have gone further than the solvent has. When you do a chromatogram in different solvents, you're going to have different RF values. And this can be really useful if you've got 2 substances that have the same RF value in one solvent, because in a different solvent, they'll probably have slightly different solubility and they'll probably have slightly different RF values. A pure substance on a chromatogram will just show up as a single spot. To do paper chromatography, firstly, you need to draw a pencil start line at the bottom of the paper. We draw it in pencil because that way it won't smudge or run, and so it won't interfere with our samples. We apply the sample to the start line, and also you're probably going to put some other things that you're going to compare it to, and we call these standards. Then we place the paper into the solvent, and it's really important that that solvent doesn't come up to the line, because if it does, then the sample is just going to go straight out into the solvent rather than being taken up the paper. You need to wait for a little while to allow the solvent to rise up the paper, and it will take the ink with it, and then you dry the chromatogram, measure the distances travelled by the different inks, and you can calculate the RF values. I can analyse the chromatogram by looking at the number of spots, which represent the number of pure substances, and then comparing them to my standards. So here, my sample, which is on the far right-hand side, contains 3 spots, and that tells me there are 3 pure substances in it. So this could be a black ink that I'm analysing, and that black ink is made up of 3 other colours. Then by comparison of the heights, I can see that my first spot in my sample is at the same height as the spot for ink C. So that means that that is one of the colours in my black ink. Then the second spot is at the same height as the spot for colour A, so it also contains A. And then my final spot doesn't match up with any of my standards, so that is a different unknown substance. Next we come to the gas tests. For hydrogen, you probably know your squeaky pop test, but it's really important that you talk about igniting the gas or setting fire to the gas. You can't just say, do the squeaky pop test. So we ignite the gas and we listen for a squeaky pop. To test for oxygen, you take a glowing splint and you put that into what you think is oxygen, and if it is, it will relight. To test for chlorine, you take some damp litmus paper and the chlorine gas will bleach it and turn it white. And to test for carbon dioxide, you bubble the gas through lime water, and if it is carbon dioxide, it will turn cloudy, it will form a white precipitate. This last bit is just for people taking chemistry GCSE or triple science, so if you're taking GCSE combined science, you don't need to watch the rest of this. Metal cations can be tested for with flame tests, and in order to do a flame test, you clean a nichrome wire with hydrochloric acid to remove anything that's already on it. Then you dip it into the sample, which is a solid salt or it could be a solution, and then you hold the wire in the clear part of a roaring flame until you can see what the colour is. A flame test can't be used to identify a mixture of ions because you won't be able to see the two colours. Say if you have a very bright pink crimson for lithium and a pale lilac purple for potassium, you'll just see the lithium colour, you won't see the potassium as well. Lithium ions produce a crimson flame, sodium ions produce a yellow flame, potassium ions produce a lilac flame, calcium ions produce an orange-red or brick-red flame, and copper ions produce a green flame. If you don't want to use a flame test, you can use flame emission spectroscopy, which is basically a larger scale computer-generated method for doing the same thing. So the sample is put into a flame and the light is given out is passed through a spectroscope. So a spectroscope can analyse that light and tell you the exact wavelengths of the radiation that's being released and how much of each type of light there is. The output of this is a line spectrum. Three advantages of using an instrumental method like flame emission spectroscopy compared to chemical tests are that they're very, very accurate, they're very rapid, so very fast, and also very sensitive, so they can detect tiny, tiny amounts of a substance, whereas if you did a flame test and looked at it yourself as a human, you're not that sensitive. You can't see if there's only a very small amount of the compound in there. We can test for certain cations in solutions by adding a small amount of sodium hydroxide, and then afterwards we may want to add excess, we may want to add more of it. If we do this to something that has aluminium ions in it, it will produce a white precipitate, and if we continue to add sodium hydroxide, that white precipitate will start to dissolve. Calcium ions and magnesium ions also produce a white precipitate, but because calcium hydroxide and magnesium hydroxide are quite insoluble, it doesn't matter if we add any more of the sodium hydroxide, they're not going to dissolve. So that would allow us to distinguish between aluminium ions and calcium and magnesium ions. But then to tell the difference between the calcium and magnesium ions, we'd need a further test, probably a flame test, where the calcium ions would give us that nice brick red flame, but the magnesium ions wouldn't. Copper 2 ions form a blue precipitate, iron 2 ions form a dark green precipitate, and iron 3 ions will form a brown precipitate. And remember, when we say precipitate, we're talking about a solid that's being formed out of the liquids, so basically it's going to go coloured and chunky. Calcium ions react with 2 hydroxide ions from your sodium hydroxide to make calcium hydroxide. I know it's going to be 2 hydroxide ions because calcium is in group 2 and forms 2+ ions. I could write the same equation for magnesium ions, copper 2, iron 2. If I was doing it for iron 3, I would obviously need 3 hydroxide ions to make it all work out. To test for carbonate ions, I add a small amount of acid, which will cause carbon dioxide gas to be released, and then I bubble it through lime water. If I have got a carbonate, then the lime water will turn cloudy because it produces a white precipitate. To test for sulfate ions, I add barium chloride, and I usually add dilute hydrochloric acid first, and the reason for this is to remove any carbonate ions, which would give me a false positive. If I react carbonate with barium chloride, I still get a white precipitate, which is the positive test for a sulfate, so I add the acid first to get rid of that. Adding sulfuric acid would be very silly because sulfuric acid contains sulfate ions, so I'd be testing for something to see if it has sulfate ions in it, but I would have just added sulfate ions to it. To test for halide ions, I add dilute nitric acid followed by silver nitrate. I need to add the acid again, same reason, because if I had any carbonates in there already, that would give me a false positive. And again, I use nitric acid rather than hydrochloric acid because hydrochloric acid contains chloride ions, so it would give me a false positive. If I do have chloride ions, I get a white precipitate. If I have bromide ions, I get a cream precipitate. And if I have iodide ions, I get a yellow precipitate. But if I had fluoride ions, I don't get any result at all. And the reason for that is because silver fluoride, which is what we're making, is soluble. So it doesn't precipitate out, so you can't see it. I hope that was helpful. Don't forget to subscribe.